Okay, good morning, everyone. As I was noting earlier, we are nearly halfway through this quarter. Well, not quarter, but halfway through this first 5-week session. By the end of today's class, 50% of our time is completed. Okay, and then the rest is going to deal with capacitors, inductors, and AC circuits. So before we move on, I want to wrap up chapter 2 with a brief recap about Thevenin and Norton. And so let's bring up the class notebook. Okay, so we did 3 examples. I want to recap by talking about the problem setup for Thevenin and Norton. Okay, as I was stating when I began the topic, this is one of the most important concepts in electric circuit analysis, where we take any large linear circuit comprised of multiple components and multiple sources, and we represent it as a single voltage source or a single current source. Okay. Now, we are not going, this is a class for non-E major, so we don't go too in-depth into the topic. But again, this is a fundamental topic that every student should be aware of. So in the final exam, when I ask you to do this, I will ask you to redraw the circuit 3 times. Once for Thevenin voltage, once for Norton current, and the third one for Thevenin resistance. Each one of these circuits are independent of each other. In the final exam, of course, I'm going to ask you to set up the problem, meaning you redraw the circuits and then you analyze. In the quiz, I won't ask you to do any analysis. Again, if you recall, the analysis is not new. There is no new analysis technique to determine the Thevenin and Norton circuits. The analysis is basically either you use node voltage or mesh current or superposition principle to analyze the circuit. The setup of the problem is what is important. So if you don't know the setup of the problem, the rest of it doesn't matter. Okay. Your analysis could be completely correct, but your final answer would be incorrect because your setup of the problem is incorrect. So again, I want to harp on this. Thevenin Norton is not a new analysis technique. It is a theorem that you apply to determine the equivalent circuit. And the concept requires you to redraw the circuit, the initial circuit 3 times. So on the quiz, I will ask you how to set up the problem, which is redrawing the circuit 3 times. Okay. And I'm going to go over how we do that. With Thevenin resistance, you remove the component if it states. You remove the component if it states as seen by, or a load resistor is representing the second circuit, or as a load for the first circuit. If it states, if the problem states, determine the equivalent circuit between terminals AB or terminals XY or a specific pair of terminals, then you do not remove anything from the circuit. This is a big difference. Okay. If the question states, determine the Thevenin or Norton circuit as seen by a particular component, then you remove that component from your analysis, which is the absolute first step right here. Okay. If it doesn't state anything like that, if it simply states between a pair of terminals, then you analyze between a pair of terminals, you do not remove anything. Now, after you do that, after you remove it, then you redraw it 3 times. Once to determine Req between those pair of terminals. So you simply reduce all independent sources to 0. Replace every voltage source with a short circuit and every current source with an open circuit, and you find Req. No sources should be present when you try to find Thevenin resistance. Any questions so far? Then when you try to find Thevenin voltage, you simply analyze the circuit to determine the voltage between the open pair of terminals. There is no further modification to be made. Please note that for Thevenin voltage and Norton current, you're starting back with the original circuit, meaning all the sources are back in the circuit, which kind of make logical sense. If there are no sources in the circuit, how would you obtain a voltage or a current, right? So all the sources should be back in the circuit for Thevenin voltage and Norton current, and you analyze it between the open pair of terminals from step 1. Okay. For Norton current, you redraw the original circuit with the terminals shorted, meaning once you establish your terminals of analysis, you short out those terminals to allow current to flow through, and then you analyze and determine the current that is flowing through those terminals, and that would be your Norton current. Let's take a 10-second pause. Let me know if you have any questions. And again, I will repeat for the nth time, the setup of the problem is the most important. If this is incorrect, the rest of your analysis doesn't matter. Any questions from anyone? Okay. What did we do here? We were asked to find Thevenin resistance between terminals A and B directly. So we didn't make any modification to the circuit. There is no component to remove. There's nothing to be done. If you need to find resistance, you disconnect all the power supplies that are present in the circuit. You replace voltage sources with a short and current sources with an open. And we find Req between A and B. And that is the Thevenin resistance for the circuit. And that's it, straightforward. When it comes to a circuit like this, which has a source, and you're asked to find the Thevenin and Norton circuits as seen by the 2-ohm resistor, or the words represents the load, as seen by the load. And then you remove that component from your analysis. That 2-ohm resistor is not part of your analysis, and we've done that right here. That's the absolute first step. And then after that, you redraw that circuit 3 times, once for Thevenin resistance, once for the voltage, and once for the current. And those are detailed and outlined here, here, and here. So let's take a 10-second pause. Let me know if something doesn't make sense. Let me know if you have any questions. Any questions? Yes. This one? It's because the 4-ohm resistor is not connected to anything at the other end. And because it's not connecting, there is no current flowing through there. If there's no current flowing through there, the voltage across that resistance is 0, which means both points are at the exact same potential. There's no current flowing through it. So voltage remains the same across both ends. And that's why it's, so it's a concept, meaning if there's a component connected and there's left hanging open, even though there's a resistance in place, current cannot flow through, but the potential of both points, the electric potential at both ends of that resistor is exactly the same. And in the next circuit, we have two sources, but the setup of the problem, again, is exactly the same because the problem statement outlines that the 17 ohm resistor represents the load, meaning it should not be part of your analysis. We remove it, keep the terminals open, and then we redraw it 3 times, once for resistance, once for Norton current, and once more for the Thevenin voltage. Okay. Please ensure that you understand the setup of this problem. Again, it's a guaranteed 30-point problem on the final exam. It will run about 4 pages in length, and it will assess everything from chapters 1 and 2. Okay. REQ, node voltage analysis, mesh current analysis, voltage division, current division, everything. Okay. The reason for the length of the problem is because it will be the same circuit that students analyze. So I will not give you a new circuit for every technique, meaning I will not give you a new circuit for node voltage and a separate circuit for mesh. Okay, students always have this fear. It's a 4-page problem. It's so long, it's going to be complicated. But it's actually easier because you analyze the same circuit for all 4 pages. Okay. Any questions before we proceed from anyone? Okay. All right. So then let's talk about source transformation. This is not something that I utilize in circuit analysis. I try to stay away from this. But again, this is a concept that students should know. We talked about how Thevenin or Norton circuits are equivalent circuits of a large circuit, right? Going back to, let's say, the beginning of the topic, right? We said Thevenin is the equivalent of that large circuit, and this Norton is also the equivalent of this large circuit. And so we can state the Thevenin and Norton circuits are equivalent to each other. And from that comes source transformation. If we have a voltage source in series with a resistor between a pair of terminals, we can convert it into a current source in parallel with that same resistance between those same pair of terminals. And out plus and out minus are simply labels. They don't mean anything in the context. It's simply label. It's X and Y or A and B. So you can transform a voltage source into a current source and vice versa. But the caveat being that the resistor must be in series with the voltage source and the resistor must be in parallel with the current source. Otherwise, you cannot transform them. And the tricky thing is that we have to keep these terminals in mind. Okay, the reason I avoid this is because it's very tricky when you have a large circuit and you're trying to transform a voltage and a current source. So I tend to avoid this technique. So I will show you what we can do with source transformation. So in this example, in figure number A, we have a circuit comprising of a voltage source and a current source. What we will do is we will break up the circuit right here. If you break up the circuit right here and we label these terminals, let's say we label them as A and B. If I label them as A and B and redraw the circuit, I can detach the voltage source on the left side and I can detach the current source on the right side. So now between these pair of terminals, these are both A and B, right? This is B and this is A. So I'm detaching, I'm cutting out on either side. I can transform the left side into a current source, and that would give me circuit shown in C. Or I can transform the current source on the right and convert it into a voltage source. That would give me circuit number B. Okay. Does that make sense? Let's take a 10-second pause. When you look over it. Any questions? No questions? Now, of course, the quantity that relates the three terms, meaning you transform a voltage to a current source or a current source to a voltage source, you use Ohm's law, V equals IR. So if we take a look at the circuit number B, what do we see? The 1 amp current source is transformed into a voltage source. And we use V equals IR, right? We use V equals IR. So it's 1 amp times 10 ohms, which gives us 10 volts. And so the current source is transformed into a resistor in series with a voltage source. Current is going in the upwards direction, meaning plus should be at the bottom. Plus should be at the top and minus should be at the bottom. Resistor value remains the same, and that's how we obtain circuit number B. Circuit number B. Similarly, if we look at the portion of the circuit on the left, we can perform V equals IR. I would be equal to 20 divided by 5, which would give you a 4 amp current source. And so that would become a current source that goes up in parallel with a 5 ohm resistor. And we can obtain circuit number C. Obviously, I'm showing the mix and match where you transform only one side, or you can transform both sides. You can call that a circuit number D if you wish. All right, let's take a pause while you think over it. Let me know if you have any questions. Yes. Yes, so the question being asked is about the current direction, and the answer is yes, because the voltage source is a plus and a minus, right? And so the current direction would also be in this upward direction, going from minus to plus. And the same concept here, because the current is going in the upwards direction, current always goes, for a supply, it goes from minus to plus. So the voltage polarity is in that direction. Let me mark it here. So since this is minus plus, current goes up. And so when you transform the voltage source, it'll have a current that goes in the upwards direction. All right, any other questions? Any questions? Does that make sense? Okay. How can we make it easier to solve with source transformation? Well, if you look at circuit B, what do we see? You have two voltage sources. Negative ends of the voltage sources are connected together. but they're not in parallel because the other ends are not connected together. Okay, so they are not in parallel. But here's the way. You apply KVL around the loop. You apply KVL around the loop, and what do you obtain? If you look at the two resistors in series, they're connected between this node on the left, this node on the right. Because the bottom node is connected together, you have a common point of reference. The voltage source on the left is at 10 volts. The voltage source on the right is at 20 volts. What is the difference between the 2 points? 10 volts. Takes a long time to do elementary school math. So you apply KVL, that is the technical explanation, but I was just showing, by the two-dimensional, one-dimensional diagram, right? One end of that resistor is at 10 volts, the other end is at 20 volts. So the difference in electric potential between those 2 points is 20 minus 10, which is 10 volts. So if the difference is, which end is plus, which end is minus? Which end is higher? 20 end is higher, right? 20 is higher than, so this is plus, this is minus. Which direction is current flowing? To the right. Current always, for a passive component, like a resistor, current always goes from high to low. So it's plus to minus, high to low. You have R1, which is 5, and this is 10. Apply Ohm's law. Apply Ohm's law. This is 10 volts. Current's flowing in this direction. You can find I1 as equal to 10 divided by 15. That's it. 10 divided by 15 would be about 6.333 something. Yeah. Does that make sense? So rather than do a complicated analysis like node voltage or mesh current, you can do a source transformation and obtain the answer in like one step. Yeah. Now let's take a pause. Let me know if you have any questions. Well, it depends. The question being asked is, if we transform it, can we just use Ohm's law? The answer is yes and no. It depends on how the circuit comes out. Remember, these are all the circuit analysis techniques we've learned. They're all tools in our toolbox. Oh, you're asking. Okay, so I misunderstood the question then. You're asking about how we obtain this 10 volts, right? How we perform the source transformation from here to here. Is that your question? Okay, yeah. So that's Ohm's law. Yes, that's Ohm's law. Yeah. All right. Any other questions? Yes. Yes. That's a very good question. So the question being asked is the I1 that we found here, is that the same I1 that is shown here? And in this circuit, the answer is yes. It again depends on how the circuit changes. So anytime you make a modification in a circuit, right, for our analysis purposes, the circuit changes. So if the circuit changes, then you have to look at the circuit and determine whether it's still the same or not. In this case, the answer is yes, it is the same. Now, if it was a different circuit, as part of a larger circuit, the source could be somewhere in the middle, and you transform it, it might not be the same. Any other questions? So let me quickly just talk about C. So when we talk about circuit number C, you would apply KCL because you have two current sources. And if you look, these are in parallel because the bottom nodes are connected together, the top nodes are connected together. So the voltage would exactly be the same. But if you apply KCL, we can have 4 plus 1 equals I3 plus I2. Two resistors in parallel, we can find Req. Req would be R1 and R2 in parallel. We find Req and we have the total current, 5 amps. We find the voltage across all 4 of these components. And that voltage would be the same for all because they are all in parallel. It's the exact same node. Once you have the voltage for all 4 components, you apply Ohm's law, you find the currents through those resistors. Makes sense to everyone? Okay. All right, let's take a break and meet back here in, let's say, 5 minutes. It's 11:03. Let's pick up again at 11:08. In the meantime, I'm still here.